Hello, good afternoon. Thank you for having me today. Okay, so what I'm going to speak about is actually how to use federated learning for collaborative intrusion detection. Without further ado, I'm just going to introduce a bit about the motivation also about doing that. You may know that in Europe, there's this NIS directive that's been extended. So now there's a second version. And so it actually involves more and more small companies as well that usually may not have sufficient security measures in place. So actually, I also have like a couple of projects that have been accepted this year that actually deals with empowering smaller companies with collaborative detection. The idea is that if you have like a managed service, that is, you have a security vendor that proposes to deploy, for example, a network intrusion detection system in your premise, you will train it at least on some of your data, and then you will benefit from the federation of all the clients of this vendor in order to improve your security. So yeah, this is just like to say why we're using AI, right? How AI can be used for improving cybersecurity operations. And so you have like the whole cycle of cybersecurity operations that has been standardized by the NIST. And at each step, you can actually ask yourself whether you need to automate some of the tasks, you need to alleviate the human load. One of the main issue, for example, with intrusion detection is that eventually you get alerts that are coming from your different systems. And these alerts have to be interpreted and acted upon by human analysts. But for example, if you have a lot of false positives, so you're going to spend a lot of time, waste a lot of your analyst time just trying to make sense of maybe something that is not an intrusion. So maybe some of you don't know about intrusion detection. So for the sake of completeness, I wanted to make a small introduction about that. So you may understand what's the concept of cyber attack anyway, and maybe something anomalous that have like adverse effects on your system, be it at the computer itself, or like software speaking, or on the network. That could be disturbing the network and eventually occasioning some of the denial of service that you may heard about. Here, for example, we have like two ways of detecting intrusion. The first one is you are absolutely sure that you know how the attack is actually carried out. And you have identified ways to pinpoint in, for example, network packets, how to detect it. So this is called like misuse detection. And normally you have heard about maybe attack signatures. For those of us that have had some antivirus deployed on our PC, we remember that, oh, every now and then I have to update the signatures. So that's it, okay? You have some signatures and you match every packet that's coming into your network with this list of signatures. So this is, I would say, quite accurate, but inefficient. And also, it has another downside is that if you don't know about a new attack, it won't be in your signatures. That's why we were always updating. And then you have the anomaly. The anomaly here, you take, as a primer that you know about your own system. You know what you have deployed. You think you know. And from the behaviors of all these systems, you are able to kind of extract some baseline. And then you look for any deviations from this baseline to understand whether there's something fishy that's going on in your system. So for us, the idea in the network is how to capture these activities. And usually we're going to just have a tap on some of the network equipment, and it's going to duplicate the network traffic to our intrusion detection system. So yeah, if we are not only looking at the network, we're looking also at some processes, some logs on the different systems. But it can be a huge volume to process. I'm going to skip a few slides anyway, sorry, because it's too long for 15 minutes. And just to show you like the usual, I would say, ML-IDS pipeline, where we do traffic capture. So I have represented, like, for example, a sequence of packets, but most of the time we're not going to decide on a single packet. So you're going to take into account that there are several packets that are exchanged between two hosts, which is actually called the flow. And we will extract some features. So there are a lot of standards also coming from the network traffic analysis community, which we got a lot of inspiration from. And provided you have already trained your system, you are going to ask yourself whether this is benign, for example, whether this is an anomaly or whether this is this kind of attack, for example. You may have like several classes of attack depending on your knowledge of the cybersecurity landscape, I mean the threat landscape. So as a classification task, well, just a few words here, but the idea is that we can also do misuse detection based on machine learning. It's just like learning the different attack classes, sorry. I mean, at least that's how I'm making the distinction. While for anomaly detection, you preferably learn on legitimate data. So your own data, you don't have to download attacks or to try to run attacks in your system. One myth is that usually people think that we can only do anomaly detection using machine learning, but I mean, as I told you, also signatures can be done using machine learning. So yeah, now into what I wanted to talk about mostly today is federated learning. So I think like I mean over there maybe wanted to do a presentation. But the idea is that we're going to distribute the computation of the model that we're going to use, for example, as a detection model. But the idea is not really distributing. It's not like I have a single data set of, for example, captured traffic that I'm going to split. Here, each client actually comes with its own local data set. Like, for example, if we are in an anomaly detection use case, they come with their own representation of what is normal traffic in the system. And they will train a local model and then send some information. Obviously, when we spoke about federated learning, we hear a lot about like it is privacy preserving. Why? Because at least at first glance, you are not sending data, right? You're only sending gradients, parameters of your models, for example, but not your own private data. And then we have, which could be, as I told earlier, the security vendor that is going to aggregate all these models in order to compute a single one that is going to be sent back to other clients. And these clients are going to use this aggregated model to do detection. What I hoped when I started this project is that we could gain some knowledge from the different participants so that overall all the participants could be immune to most attacks, okay, or could understand. Yeah, I lost the sorry. So I'm trying to speak a little bit now. And so also, for example, you think about like legitimate behaviors. So you could learn about all different legitimate behaviors. And one of the, I'm talking here? Oh yeah, I think I can hear myself. So for example, another added value or in another use case we thought about is, for example, in very mobile use cases where you have devices that are actually going from one subnetwork to the other. And if you do like such kind of distributed detection, well, you will see like new devices coming into your network. And maybe you think it's an anomaly or a compromised device, and you flag it as an anomaly or an attack. Here, the idea then is that it has been learned by another collaborating subnetwork, and then you gain this information and you prevent having false positives. So we look into how to do aggregation. And one of our major motivation was actually that if you use like these standard ones like Fed average or Fed SGD, well, they are really fragile when it comes to imbalanced data. Why? I mean, you see a lot of people doing federated learning IDS, and they claim to have good results, but they do distributed training. They don't do the real use case that I'm trying to present here. That is, each client comes with its own local private data, okay? And this data may represent different legitimate behaviors, may represent different kinds of attacks. And so this means that, in a sense, some of the clients, they know quite nothing about some of the legitimate behaviors. They know quite nothing about some of the attacks. And if you're using FedAVG, well, you're going to, well, have try to improve the overall accuracy, but it's quite fragile when you have like extreme imbalance and some clients that have no knowledge of attacks. There are actually other works, FedProx, Kfold, always trying to improve accuracy, but for example, Kfold also looked about the problem of data drift between local participants. Yeah, so this is the federated learning IDS. I'm not going to reintroduce that. I think I've already done it earlier. But just to say that in the state of the art, they don't like really take into account the non-IDness of the data. And you will see, as I said, that there's many aggregation methods that are trying to really look at the varying proportions of the different attack classes, but it's not necessarily, I mean, it's still not efficient when you have like no knowledge of some of the attack classes. I may actually introduce a really big assumption that I make here is that, for example, if we do federated attack detection, everyone knows about all the attack classes. They just don't have data to train with, okay? So it's really a big assumption because this means that at their local model, they have an output neuron, they have an output node for every attack, even though they don't have training data for this specific attack. So what we used is actually the federated prototype learning. The trick here is that for every class of attack that we know about, if we have some of the data, we are going to project the data in a latent space and compute a representative of this cluster. And this will be called the prototype. The prototype itself has no real meaning in the problem space, but it can be easily exchanged with the aggregated server that will then aggregate all prototypes in the same latent space because we have like the same representation and compute the aggregate of this prototype and then send it back. If you don't have any data about a given attack class, that doesn't matter because you will have like an empty cluster, but then you will receive the prototype, I mean, the average prototypes of all the other participants. And then you will learn a new attack that you didn't know about before. And we had actually good results that were actually compared on 2 data sets. Well, these are not like real, I mean, they are real life or not, depending on how you actually define real life data sets. But there are data sets that were collected in IoT environments and 5G environments, for example. And we were able to actually outperform most of the state-of-the-art federated learning IDS. But what was also important for us is the graph that you have at the bottom, where we actually had some of the clients that didn't know about, for example, 2 attack classes, but really nothing. They have no training data. So they cannot make out where to place their cluster in the latent space, but they don't care because they will eventually receive this information from the aggregated model. And we have actually used Cerberus, which is based on Fed average, and our own Protean here in orange. And we were able to show that we were learning something and then be able to detect the attacks afterwards. So there are still open issues. Some of the open issues here are actually dealt with in the paper. As I said, for the zero-shot learning of unseen cyber attacks, it's actually dealt in the paper. And the investigation also of the potential privacy leakage, because we're exchanging more information than other federated learning aggregation function, because we sent also the prototype. But as I said earlier, the prototype itself doesn't really leak much information about the training data. So thank you for your attention. I think it's that. The paper is actually on arXiv also. So it's a paper of Sarah Chenoufi, and you can find the information here. It's Protean. Thank you for your attention.
Okay, I want to make a couple of comments. So I'm sure you're well aware, but this, using AI for attacks is absolutely all the rage and moving at a very, very fast speed. And all the AI companies are using, all the public CVEs to train models. And that's not for the kind of what you're talking here. That's more for detecting vulnerabilities in code. But that's working pretty well. And it's based on public data that is trains a centralized model that can actually uncover all kinds of complex nuances. So I ask myself in your context here of anomaly detection, whether actually is federated learning even the right approach at all? Because there are some public data sets, you mentioned those. If each node knows about one attack, but is willing to share that attack, then you can use that and couple it with the other big trend, which is synthetic data, right? So let's say I have some distribution of what I think attacks look like, and I can take from 4 or 5 data sets. I can add into that, take all your favorite probability models, add edge cases for everything, even if you don't have examples for it, and train an LLM to catch it. So, I mean, I'm wondering, do we even need federated learning anymore? Because I think LLMs will kill the problem, and synthetic training data can enormously augment what we already have in terms of the public data. So,
yeah, that's a really good question, and it's always, I mean, we always need to have like a critical view, right, about what we are doing and whether it's still relevant. As a matter of fact, I also work on generating synthetic data for traffic detection. Where we're at right now, we were actually generating feature vectors, okay, that are flow representation of what we want to detect. And it's pretty good. I mean, at least based on the framework that we have also developed in order to compare ourselves. And we're not using like really big, actually, ML algorithms. We're using a Bayesian network. But the Bayesian network has a cost in terms of training and also in terms of representation. For example, we had like many issues with the granularity of some of the features. If you have like many values for some of the features, there's a combinatorial explosion. But coming back to why federated learning would be interesting, as you said, I mean, we're not looking for vulnerabilities, but usually when you have a cybersecurity approach, the first thing you do is risk analysis. You deploy all the countermeasures that you can afford, or that may be also environmentally acceptable. And then you have like residual risk. Residual risk, usually you need to do intrusion detection. And because you're going to act after that when you know that you're under attack. One of the things I may agree also with you is that the kind of data sets we are actually evaluating are not really representative, because we try to detect all the attacks while it's not really necessary, okay? But I mean, that's what we have at hand. And in order to be comparable with other works in the field, we use the same data sets. But if you take my approach of like okay, residual risk detection. The thing is that this residual risk detection, why can we not defend against it? Maybe because they are emerging, maybe because there are not enough knowledge. And if we can do like some kind of collaborative anomaly detection, we also may have false positives, I'm sure. This is something also that we need to pursue in this work to understand the amount of false positive that we're going to generate. But we still have the ability to anticipate. The first intuition was we always hear about like this incident there, and then some days later, another company gets actually attacked with the same threat. And the smaller the company, the more vulnerable it is. So we thought about, okay, if we can get this information and then just spread it, maybe we can actually stop the propagation.
Yeah, so I understand your point about residual risk, but one other thing I didn't understand in your presentation, you talked about end nodes that have an example, right? That maybe nobody else has, and so this can be learned indirectly through federated learning. But how does an individual node know that this was an anomalous event if it has never communicated with anybody else? It's not pre-labeled necessarily.
Yeah.
How does it know that this should be part of the contributing that to the algorithm?
Yes. So that's yeah. That one of the problems is that in the work we had like the two use cases. Either we do anomaly detection or we do attack detection. So this the evaluation was only done with attack detection. So we don't pretend to know about anomalies in advance. We only pretend that we know about the attacks in this evaluation. But I gave another example, which is trying to prevent false positive when you have actually anomaly detection. Is about this device moving, across networks. Yeah, but these are, sorry, okay. That was misleading. I apologize.
Anybody else?
So quick follow-up, actually, somewhat related to the question Nina asked. My understanding from what you presented is that the generated learning and the photographs get generated. We essentially assume that all the participants are in some sense collaborating, are using the same learning models, right? That may not be happening in practice, right? You may have a bunch of different users, they all have their own sets of tools, and they may be generating, they'll be using their data and training some models, but they may not be using the same training algorithm and so on, right? Are there ways for you to sort of take any arbitrary output, sort of features, whatever that they produce, and convert it to something that will then be like a common API, to use a maybe an improper word, but that can allow then that kind of combination, or is it not feasible?
Yeah, these are really good questions. These are part of the assumptions also that we have. First, I wanted also to acknowledge the other colleagues in this work. There's Yufei Han from INRIA, which actually helped us with designing the whole approach about federated prototype learning, and Emiliano De Cristofaro from UC Riverside. And this is the work of Sarah Chenoufi. I went to see Yufei one day a couple of years ago, and I asked himself, I have this intuition that, okay, different people, they know about attacks, okay, but I want them to exchange information. That's when we came with the term knowledge sharing. Maybe it's also in the literature. Maybe we didn't really invent that. But I asked him, are we able to do knowledge sharing? He said, okay, let's just sit, let's go in my office, and we work on the whiteboard to do that and to have like this kind of protocol. But of course, there are a lot of assumptions. One of the assumptions, two of the assumptions. The first is we work with the network flow abstraction. So this is coming from the network traffic analysis community. So this allows us to say that everyone knows how the data is represented, okay? The second big assumption, as I said, is that everyone knows about the different attack classes. At first, I asked Yufei, are we able to have heterogeneous models at each client? And we said, yeah, let's first assume that everyone has the same model, that is the same number of inputs. The number of inputs is actually based on the flow abstraction. And we have the same number of outputs, that is we know about all the attack classes. These are actually big assumptions, but I hope that in the future we'll be able to be working, for example, with will actually alleviate the output abstraction and having like, for example, unknown classes. There's a work from a team in the University of Western Brittany, I guess, or maybe, I mean, it's Robin Duras. Robin Duras from Naval Group. He used contrastive learning, and the trick with using contrastive learning is that he said, I'm going to add an unknown attack class. And by contrasting the different clusters, whatever I cannot put in my clusters, I'm going to put it in the unknown class. And actually that worked well, of course, for the data sets that we have in the community. But yeah, and I got inspiration from that. Yeah.